So in yesterday's class, we have seen what LVDT means. Okay. So LVDT means linear variable differential transducer. Linear variable differential transducer. So why the name linear variable differential transducer and how it is used and what about its working? Okay. All these concepts we have seen in yesterday's class, right? So
धन्यवाद.
So coming to LVDT, see here, see here, it is a linear variable differential transducer. Linear variable differential transducer. Okay, not differential transducer, it's a differential transducer, right? Why? Because output is in differential form. Output is in differential form. So this is the primary winding, this is primary winding, and these are secondary windings. I call this secondary 1 and I call this secondary 2. So secondary 1 and secondary 2 are arranged in such a way that the currents through secondary 1 and secondary 2 are opposite to each other. Okay, the currents in secondary 1 and secondary, this is the current to secondary 1 and this is the flow of current through secondary 2. So both are in opposite direction such that we will get differential output. We will get here differential output. Okay, we get here differential output, right? So now output V1 minus V2 is the output voltage, and the output voltage is proportional to this core moment. Okay, so the same diagram here is represented like this. Okay, this is the top view of the instrument or cut section view of the instrument. Okay, so this is primary coil, this is primary coil, right? And these two are secondary coils. These two are secondary coils. This is the primary one. Okay. So in between the core is suspended. The core is suspended here. Okay. Through springs. The core is suspended here through springs. Okay. So there will be a housing like this. There will be a housing like this, right? There will be a housing like this. So I am giving primary supply here. I'm giving primary supply here. So I am giving displacement to core from outside. Displacement to core from outside. Okay. So that output voltage is proportional to displacement. Output voltage is proportional to displacement here. Okay. So if you see here, this is a primary coil and these are secondary ones. These are secondary ones. Okay. When the core is in center position, when the core is in center position, right? So what will happen? What will happen? Through the supply voltage, flux will be developed. Flux will be formed here. Okay. Here the flux will be formed here. See here in secondary 1 and secondary 2, in secondary 1 and secondary 2, the windings must be same. Okay, and the cross section area of conductor must be same throughout the windings. Okay, so the dimensions of secondary 1 is exactly equal to dimensions of secondary 2. So what will happen when core is in center position? When core is in center position, what will happen? Flux will be formed here. Okay, so the core is equally spread through secondary 1 and also secondary 2. What will happen? When the flux cuts the conductor, when flux cuts the secondary windings, EMF will be generated. EMF will be generated. How? The amount of flux cutting secondary 1 is equal to the amount of flux cutting secondary 2. Okay, the amount of flux cutting secondary 1 is equal to the amount of flux cutting secondary 2. Why? Because the core is at the center and the dimensions of secondary 1 is equal to dimensions of secondary 2. Means number of windings secondary 1 is equal to number of windings secondary 2, and also the diameter of secondary 1 is equal to the diameter of secondary 2. So here current I1 will be developed. Current I1 will be developed. So the voltage here is V1, let us suppose, and here the current I2 is developed. I2 is developed here. Since I1 equal to I2, V1 is equal to V2. Let us suppose V2 is the voltage here in the secondary winding. Okay, V2 is the voltage in the secondary winding. V out is equal to V1 minus V2. Output is in differential form. Output is in differential form such that output is equal to 0. Why? Because V1 equal to V2. Since I1 equal to I2. Since I1 equal to I2. Okay. So for example, let us suppose the displacement what I want to measure is applied to this core. So let us suppose the displacement is towards upside. Upside. So what will happen? Here, large amount of flux will be there, and this flux cuts the conductor. Even though there is a flux present here, the medium is insulator here, air core. Okay, air here, sorry, air here. So here, very less amount of flux cuts this conductor, or negligible amount of flux cuts this secondary windings. Okay, secondary 2. So more amount of current will be there in secondary 1. This is I1, so that V1 is high, and very less amount of current is there in secondary 2. So I2 is almost 0, but there will be very small currents flow in this secondary 2. So let us suppose this is V2, and output equal to V out equal to V1 minus V2. Output equal to V1 minus V2 gives me some positive value. Gives me some positive value. Okay, this sign gives me the direction of displacement, and the magnitude here gives me information about amount of displacement. Okay, so till this concept we have discussed in yesterday's class, right? And so these are the characteristics. This is core position, means displacement here. Displacement versus output voltage. Displacement versus output voltage. If displacement is 0, output voltage is 0. If displacement is 1 mm, the output is also corresponds to 1 mm only. Okay. Let us suppose output is now increased. Let us suppose the input is now increased to 3 mm. 3 mm displacement. Then equal amount of output will be there. So the amount which was increased here is proportional to the amount which was the difference here. So the difference in the input exactly is the difference in the input is exactly shown at the output. Okay, so output is in voltage form and input is in displacement form. If we draw a graph between input and output, the graph is linear graph. The graph is linear graph. Okay. Now, one point to remember is this that see, every instrument has some range. Every instrument has some range. Okay. Beyond that range, if we use that instrument, it may show non-linearities, and afterwards it show wrong values, and the instrument may be damaged. So the range of instrument is very important. Why? Because the input must be within the range of working range of instrument. Okay, or I have to use instrument which can measure the input. Means మనం మెజర్ చేసే ఇన్పుట్ యొక్క మ్యాగ్నిట్యూడ్ ఇన్స్ట్రుమెంట్ మనం ఉపయోగించే ఇన్స్ట్రుమెంట్ రేంజ్ లోపే ఉండాలి. ఓకే, మనం ఉపయోగించే ఇన్స్ట్రుమెంట్ యొక్క రేంజ్ లోపు మన తీసుకునే మెజర్మెంట్ అనేది ఉండాలి. ఓకే, సో రేంజ్ దాటిపోయి ఇన్పుట్ ఇస్తే దెన్ ఇట్ విల్ షో నాన్ లీనియారిటీస్, ఆర్ ఇట్ విల్ షో ఎర్రర్ వాల్యూస్, ఆర్ ద ఇన్స్ట్రుమెంట్ మే బి డ్యామేజ్డ్. So this is the range of instrument for which I am using this instrument. This is the range of instrument. Beyond that range, if I use the instrument, it shows non-linearities. It shows non-linearities, means it will show error values. See here, within the instrument working range, the sensitivity at the slope at every point is same. Means sensitivity at all points is same. Sensitivity at all points is same. Since sensitivity is same, the instrument has high linearity. High linearity. Okay. Always want to make system linear. If you make system linear, then what will happen? మనం ఇన్పుట్ ఎంత పెంచితే అవుట్పుట్ ఎంత పెరుగుతుంది అన్న అవగాహన మనకు వస్తుంది. ఓకే. తర్వాత the most important thing is, if the system is linear, even though if there are any errors in the system, in the instrument, then the error must be that the error should be error will be static error only. Means the error doesn't change. If the error doesn't change throughout the range of instrument, then what will happen? I can get exact value, or I can calibrate the instrument. So if the system is linear, I can calibrate the instrument so that I can minimize the errors. So that I can minimize the errors. System linear ga lekapote, system linear ga lekapote, then I can't calibrate the system. System మనం calibrate చేయలేమండి. జీరో అండ్ స్పాన్ కాలిబ్రేషన్ మనము చేయలేమండి. సో జీరో అండ్ స్పాన్ కాలిబ్రేషన్ చేయలేకపోతే then the error will be not a constant value. It will be a dynamic error, and it will show every time wrong values. Okay, means the repeatability and reproducibility will be very, very less. Okay, so this is about the characteristics of the graph. Okay, and now uh, since the core is suspended here. Okay, the core is suspended here. Suspended ఏంటమ్మా, హ్యాంగ్ అయి ఉండవు అనమాట. ఓకే, ఈ కోర్ హ్యాంగ్ అయి ఉంటుందండి హౌసింగ్ కి. ఓకే, ద హౌసింగ్ ఆఫ్ ద ఇన్స్ట్రుమెంట్ కి కోర్ హ్యాంగ్ అయి ఉంటుంది అనమాట. ఓకే, ఇట్ ఈస్ హ్యాంగ్డ్ త్రూ, ఫర్ ఎగ్జాంపుల్ లెట్ us suppose this is housing. Let us suppose this is housing of the instrument, right? And the core is suspended like this through springs. These are springs. They are not resistances. These are springs. Okay. So, for example, if the stiffness of spring is lost here due to temperature or high vibrations, let us suppose, then what will happen? The core will not be exactly at the center. Okay, means I am not applying any input here. I am not applying any input here. Input for the instrument is displacement. Input for the instrument is displacement. I am not applying any displacement here. Okay, such that the core will be in center position. Therefore, output should be 0. If input is 0, output must be 0. Okay, it is one of the main it is one of the important statements for stability, right? BIBO, bounded input, bounded output, and if input is 0, output must be 0, right? So I am not applying any input here, thus that output should be 0. When the output equal to 0, when the output equals to 0, when the core is at center position, when the core is at center position exactly, then output will be 0. If the core is not at center position by any chance, then the output will not be 0 volt. Then the output will not be 0 volt. Okay, మరి కోర్ సెంటర్ పొజిషన్ లో ఎప్పుడెప్పుడు లేకుండా ఉంటుంది అంటే the core is suspended here through springs. Okay, the core is suspended here through the spring. So what will happen if the stiffness of spring is lost? If the stiffness of spring is lost, then what will happen? The spring may elongate much more. So these springs are used to make the core lie at center position only. If the stiffness of spring is lost or spring యొక్క స్టిఫ్నెస్ కోల్పోతే సాగిపోతుంది అప్పుడు కోర్ సెంటర్ పొజిషన్ లో ఉండలేదు సో కోర్ కింద కానీ పైకి కానీ మూవ్ అవుతుంది డిపెండింగ్ అపాన్ ది స్టిఫ్నెస్ ఆఫ్ స్ప్రింగ్ ఓకే సో what will happen output will be induced now output is not zero now output may be a 1 volt or it may be a 2 volts likewise okay so output some positive or negative value I will get positive or negative value I will get okay it is dependent on the direction of movement of core even though I'm not applying any input ఏమి అప్లై చేయట్లేదండి కానీ స్ప్రింగ్ కనుక స్టిఫ్నెస్ కోల్పోతే అప్పుడు ఏమవుతుంది అంటే ఈ స్ప్రింగ్ సాగిపోతుంది ఓకే స్ప్రింగ్ సాగిపోతే ఏమవుతుంది అంటే కోర్ మూవ్ అయిపోతుంది సెంటర్ పొజిషన్ లో ఉండదు కోర్ కొద్దిగా ఇటు పక్కకో లేకపోతే ఇటు పక్కకో మూవ్ అవుతుంది core ఇటు పక్క కొద్దిగా మూవ్ అయితే కనుక I will get positive voltage at the output even though I'm not applying any input core ఇటు పక్కకి మూవ్ అయితే then core ఇటు పక్కకి మూవ్ అయితే then output will be negative voltage okay so this I have to consider okay so it depends upon elongation of spring and also second important point is these LVDTs I should not use in high vibration environments okay why because due to vibrations resonance effect will occur such that even though I'm not applying any input here what will happen the core tends to vibrate like this if the core tends to vibrate like this then output will be induced so these are the two phenomena I will get output even though I don't give any input okay and this is explained in this graph here see here I'm not applying any input I'm not applying any displacement is zero here okay even though the displacement is zero I am getting some voltage here okay this voltage is called residual voltage this is error okay this voltage is called residual voltage okay forget about this I don't want to consider now so this is the residual voltage okay ఈ voltage ఎందుకు వచ్చింది even the displacement is zero the core is not lying in the center position this is the output voltage E naught okay even though the displacement is zero the core is not lying at a center position why because due to vibrations or it may be due to vibrations or it may be due to elongation of spring due to temperature etc or the reasons okay ఈ రీజన్స్ వల్ల నాకు అవుట్పుట్ వస్తుంది ఓకేనా అండి బట్ ఈవెన్ దెన్ సిస్టమ్ ఈజ్ లీనియర్ system is linear okay if I am giving this much input this is the output if I am giving this much input this is the output okay so what I have to do is I have to correct these values why because I have zero error here okay I have zero error of residual voltage why because even though I'm applying zero I am getting here some voltage let us suppose Let us suppose at 0 input, I am getting 1 volt as output. Okay. If I give 1 mm as input, 1 mm as input, it will show 1 volt, but it is showing now 2 volts. Why? Because there is a error of 1 volt. If I'm giving 2 mm as input, 2 mm as input, I am getting 3 volts as output, but I have to get 2 volts only. Okay, 1 mm దగ్గర 1 volt రావాలి. ఎగ్జాంపుల్ చెప్తానమ్మా, 2 mm దగ్గర 2 volts రావాలి. కానీ 1 mm దగ్గర 2 volts, 2 mm దగ్గర 3 volts, 3 mm దగ్గర 4 volts ఇలా వస్తున్నాయి నాకు. ఎందుకని అంటే నాకు 1 volt ఇక్కడ ఎర్రర్ ఉంది కాబట్టి. This correction factor I have to apply everywhere throughout the readings అన్నమాట. Okay, this is called residual voltage. This is called residual voltage or zero error rate it is called. Why? Because due to misplacement of core position. Okay, due to above said values, problems, right? And now, so what are the advantages of this LVDT? What are the advantages of this LVDT? So, LVDT is highly used in instruments to measure displacements in the industries, and also uh, to measure alignment of wheels in car industries. Okay, సో ఇప్పుడు మనకి కార్ తీసుకున్నాం అనుకున్నాం, కార్ కి 4 వీల్స్ ఉంటాయి కదా, ఆ 4 వీల్స్ యొక్క అలైన్మెంట్ కరెక్ట్ గా ఉండాలండి. అలైన్మెంట్ లేకపోతే ఏమవుతుందండి అంటే టైర్ రొటేషన్ అనేది కరెక్ట్ గా ఉండదు, వంకర తిరుగుతూ ఉంటుంది. సో కార్ కూడా ఇట్ విల్ జనరేట్ సమ్ వైబ్రేషన్స్ అన్నమాట. ఓకే, విచ్ గివ్స్ డిస్కంఫర్ట్ ఫర్ ది యూజర్స్. సో ఇట్లా వీల్ అలైన్మెంట్ 1 mm కూడా తేడా రాకూడదండి. సో అలాంటి చోట్ల నేను ఎగ్జాంపుల్ చెప్పాను మీకు, కంట్రోల్ వాల్వ్. ఓకే, if I am using a control valve, then uh, a control valve actuated displacement I have to exactly measure in order to control the input parameter. ఓకే, సో ఇన్పుట్ పారామీటర్ అది ఫ్లో అవ్వచ్చు, ప్రెషర్ కంట్రోల్ వాల్వ్ అవ్వచ్చు, అది టెంపరేచర్ కంట్రోల్ వాల్వ్ అవ్వచ్చు, లేకపోతే ప్రెషర్ కంట్రోల్ వాల్వ్ అవ్వచ్చు, ఏదైనా అవ్వచ్చు. కంట్రోల్ వాల్వ్ అన్నది ఆ కంట్రోల్ వాల్వ్ యాక్చువేటర్ పొజిషన్ ని బట్టి ఆ టెంపరేచర్, ప్రెషర్, ఫ్లో, లెవెల్ అన్నవి మనము కంట్రోల్ చేసుకుంటూ ఉంటాం అనమాట. కాబట్టి ఇట్లాంటి డిస్ప్లేస్మెంట్స్ మెజర్ చేసే చోట మనము ఎల్విడిటీస్ ఇండస్ట్రీస్ లో చాలా ఎక్కువగా ఉపయోగిస్తామండి. Why? Because they have several advantages. Okay, so one of the advantages is low power consumption. One of the advantages is low power consumption. Just it will take 24 volts. Just it will take 24 volts to give output, to generate output. Okay, it has very low power consumption, right? And it is highly sensitive. It's highly sensitive. Even if you give 1/10 of a mm as a displacement, the output voltage will vary. The output voltage will vary. Okay, it has good ruggedness, means ability to withstand load. Means sudden changes ఏమన్నా వచ్చినా సరే, the instrument doesn't wear and tear. Okay, and it has good repeatability and reproducibility and accuracy. Accuracy is very high, repeatability is very high, reproducibility is also very high for LVDT. Okay, and it has a very wide, there are several types of LVDTs, so it is available in wide range, and it has low hysteresis, very low hysteresis. Okay, it has very low hysteresis. So what is hysteresis? What is hysteresis? So let us suppose I am plotting input output characteristics here. Okay, let us suppose for your better understanding, I am taking a voltmeter. I am taking a voltmeter, means a voltmeter is an instrument which is used to measure voltage. Means I am giving here voltage as input, voltage as input, okay, and voltage as input here. This voltmeter, it is measuring device only, okay. Voltage as input and voltage it will show as output. Means if I give 1 volt input, the meter should show 1 volt exactly. If I give 2 volts as the input, the meter should show 2 volts exactly. If I give 10 volts as input, the meter should show 10 volts exactly. Okay. If I give 10 volts as input, if I give 10 volts as input, meter should show 10 volts exactly. It should show 10 volts exactly. But if I if I withdraw the input, but if I withdraw the input, means input is suddenly now made to zero. Now input is suddenly made to zero. Input is not zero. Then then this graph, the voltmeter should show me zero in this direction. Okay, means when I am giving input, I am increasing input. I am giving 1 volt as input. It is showing 1 volt as output. If I am giving 2 volts as input, it is showing 2 volts as output. If I am giving 3 volts as input, it is showing 3 volts as output. If I am giving 4 volts as input, it should show 4 volts as output. And now, if I withdraw the input, if I give 0 volts now, then then this should be the direction that the instrument should come to zero. Again, it should come to zero like this. But the output is not zero exactly like this. Okay, slowly it will come to it will come to zero, and again it will make some oscillations around zero, and it will increase again, and after some oscillations it will settle down to zero. It will settle down to zero. This property is called hysteresis. So if hysteresis is there for instrument, then the responsive time of instrument is very less, very less. So this type of instrument is not suitable for fast changing inputs. So this is called hysteresis. And this is the unwanted, it is the unwanted characteristic for any instrument. Even though if it is a LVDT or a voltmeter or a meter or any other meter, any, or any other meter. Okay, hysteresis is a unwanted characteristic. It is. So the advantage of LVDT is it has a very low hysteresis. It has a very low hysteresis. So what are the advantages of LVDT now? It will take low power, it is highly sensitive, and uh, it is a linear device. Okay, it has a high ruggedness, means it has a high ability to withstand loads. It has high ability to withstand loads. Okay, and it is available in wide ranges, and it has low hysteresis. Low hysteresis means good settling time and good speed of response time. Okay, and this instrument has a good resolution also. Good resolution. So what do you mean by resolution? Smallest measurable input is called resolution. So this instrument can measure 1/10 of displacement also. So very small displacements also this instrument can measure effectively and efficiently without errors, without errors. Okay, and the calibration of LVDT is also very easy. Even though there are some errors, they they may be overcome by good calibration. So calibration of LVDT is also very easy. Okay, so these are the advantages of LVDT. Okay, and what are disadvantages then? What are the disadvantages then? There are some disadvantages also for LVDT. Okay, so first and most main important disadvantage is it is not suitable in high vibration environments. It is not suitable in it is not suitable for high vibration environments. If there are any vibrations, then what will happen? Since the core is suspended, the core will tend to vibrate. The core will tend to vibrate. If the core tends to vibrate, then it will show some output voltage even though the input is zero. So it is the major important problem for me if I use LVDT. Okay, and second most important effect is temperature. Okay, since LVDT has some springs embedded in it in the instrument, so what will happen means due to temperature, the core length may increase, or due to temperature, the stiffness of spring may decrease. Okay, the stiffness of spring may decrease. So temperature affects the performance of LVDT. If temperature is high, then very high, then it will show some wrong errors. Okay, but this LVDT can withstand from uh, 20 degrees centigrade to 70 degrees centigrade. 70 degrees centigrade. This is the temperature range. And there are some LVDTs which can withstand up to 100 degrees temperature also. 100 degrees temperature, 100 degrees centigrade temperature also. Okay. From 20 or 10 degrees centigrade to 100 degrees centigrade also it can withstand. Means these LVDTs has good temperature shielding also. But even then, if the temperature increases beyond the limit of beyond the limit, then it may show some error values. Okay, this is the normal temperature ranges in industry setting. If you take thermal power plant, then ash handling system, the pipes which are in ash handling system are generally at 150 degree centigrade temperature range, 150 degree centigrade temperature range. And if you go to a boiler, then the temperature of steam is around 525 to 550 into 525 is the normal temperature range which industries will maintain to uh, transport steam from boiler to turbine. Okay, so these are the pipeline. These are the temperatures at which the pipelines are maintained. So these control valves are mounted, or these LVDTs are mounted on these pipelines, which which will take these much temperatures. So there are some temperature effects also, right? And the most important thing is it's sensitive to stray magnetic fields. Sensitive to stray magnetic fields. Okay, so these are the disadvantages while using these LVDTs. Okay, so what I have to do in order to minimize these disadvantages, in order to minimize these disadvantages, means proper shielding must be there for LVDT. Okay, proper shielding must be there for LVDT such that the vibrations are minimized. The vibrations are minimized, and the temperature effects will be low. Okay, so proper shielding must be maintained here. Otherwise, it have a plenty of advantages in industries. Okay, Mostly LVDT is used mostly as a secondary transducer. Okay, mostly LVDT is used as a secondary transducer in industries, right? So this is all about this LVDT and what are the applications means. Just now I told you now, this LVDT is mostly used as secondary transducer, and this LVDT is used to measure displacement, okay, pressure, displacement, pressure, force, weight, etc. But mostly this LVDT is used to measure displacement and pressure, displacement and pressure. Okay, why? Because there are plenty of instruments to measure weight and force also. Okay, so mostly it is used to measure displacement and pressure, and we can use it to measure force and weight also. Okay, so mostly it is used to measure displacement, right? From 1/10 of millimeter to a few centimeters. Okay, this is the range of the LVDT. So this is about LVDT, right? Any doubts?
No, sir.
Is it clear for everyone?
Yes, sir.
రైట్ ఈ కాన్సెప్ట్స్ అన్నీ మీకు ఏకే సాహని అనే బుక్లో బాగుంటాయమ్మా. ఇఫ్ యూ గో టు కాలేజ్ ఆర్ ఇఫ్ ఎనీ ఆఫ్ యువర్ ఫ్రెండ్స్ గో టు కాలేజ్, దెన్ ప్లీజ్ బీ అవైలబుల్ విత్ ద టెక్స్ట్ బుక్. ఓకే, ఏకే సాహ్ని, SAWHNEY, ఏకే సాహ్ని. ఓకే, ఫర్ ఫస్ట్ 3 units ఐఎమ్ ఫాలోయింగ్ ఏకే సాహ్ని. ఫర్ లాస్ట్ 3 units ఐఎమ్ గోయింగ్ టు ఫాలో HS కల్సి. ఓకే, is it okay for everyone? Shall I wind up the class?
Yes, sir.
Right. This is all for today.